So we're going to continue working with use of the tables. And again, we looked at special case of normal distribution that is called standard normal. So we have curve in the shape of a bell, which is a symmetric through the line where mean is equal to 0. For the standard normal, mean is equal to 0. That's where the maximum is being attained. And we can also see that total area is given to be equal to 1. So half of area will be on one side as well as another half will be on the other side of this bisecting line, this breaking curve into two halves at 0. And again, this is standard normal, so its standard deviation is also equal to 1. That's what they actually say here. Mean is 0, and the standard deviation is equal to 1. So if I try to do the problem, let's say exercise number 15 to start, it says find the probability that, I say, where does it say find the probability? That's where it says here. Find the probability that greater than negative 233 is a reading of whatever thermometer. So we need to find the situation that unknown, which is z. Since it's a standard normal distribution, we have z-axis to identify that fact, which is greater than negative whatever 233. And to do this, I need to locate tables for this standard normal distribution. So last time I shown you how I got those tables. I was able to look at the Google search and typed Triola table. And when I go for it, I guess the first selection, formulas, tables, can be opened. And so choice 1 is usual when you look for this in a Google search engine. It just takes a little time, but we'll be patient. And in the center of this leaflet, we can find that normal distribution. So it's quite specific. It's not that yet. I think I skipped it. Here it is. Chi-squared. No, it's not that. I think I missed it. Here it is. So when you are working with negative z, like minus 233, there is a page with negative tables. And the other page is in the case when you have a positive values of z. So for a negative 2.33, I'm going to need to use that special row and a column approach, just like we did that last time. So if you have 300s, because that's 2.3 and 300, so I separately look at the column under 0.03, and then the row negative 2.3. So the row and the column are gonna meet right here at the area, which is gonna be area to the left. So if I gonna take a look at the area from negative 2.33. So it is negative, it's less than 0, so it's going to be someplace here on the left from 0. Then the tables will always give me the part to the left. And that's what it says, area from the left all the way to negative 233. And the number we have found is 0.033. That's not the area they want because they need to see when it is greater, right? And to get the remaining part, we use the fact that we have the whole area equal to 0. So that 0.0099, put 3399. Should be careful. Concentrate, I guess. So I need to subtract that 0.0099 from the entire area from 1. And that's how we always find area from that z-score to the right and the other side. And you can either use a calculator or try to subtract and get something like 0.9, right? That's what we're gonna subtract. So it's 9901. So you can, of course, use your scientific calculators to subtract from 1 the given area. So it's good to realize that by the z-score, which is always composed by using the part of it as element on the first column and the other part, the part of hundreds, as the element under 0.03. So where this row was -23 will meet the column, right? That's the area.
Professor, can you please post again the link of this table?
Sure. So I can get this link here. Yeah, absolutely. So we can put this in chat to everyone. And again, for those who just posted. So for those that are not here, definitely cannot see the chat. If you watch the recording, all you need is just to go to search and type Triola table. I'm doing a Google Chrome search and choice 1. It's not hard, choice 1. By clicking that, it will bring you in this pages right away. So that's, I guess, the way to find it. And maybe a good idea will be to bookmark. There's a little star after you opened whatever you need. You can bookmark. So click on that start and you'll save this link among your bookmarks. So bookmarks, if you want to open a new page, you will be able to go through your saved bookmarks and right away select the one that's called Triola tables. That's alternative way to remember it. So don't need to remember anything, just save it would be a good idea. So no problem. Yeah, if you're late or you're never able to come in, check the recording. I'm recording the lectures and email them to you. So it's always link to Zoom recordings in your emails that I always send after the lecture ends. So you can find this in your emails, just need to, I guess, read it sometime after class. So it's fine, you don't need to be here. I know there are various circumstances, and I totally respect those. So anyways, we got the answer. What they wanted was the, back to the textbook. They wanted to know the area, which is a synonym for us, probability from negative 233 for greater side to the right. So that area is always found by subtracting from 1. So use the tables. Well, not everything is that perfect, some people say. For example, if I try to do problem 26, and here there'll be assumption that you are not going to be able to find in your tables. So in exercise 26, they want to find the case when something is less than negative 3.61. So less, what's less? Well, z-score is less, and the probability is what I need to find, as usual. Well, so I'm going to make a picture once again. Please notice that the region we try to locate, if again 0 is someplace in the middle, will be to the left of that 0, 3.61, and it is actually so-called a little tail that we need to find the area of. And when you go back to your tables for negative values of z, so it looks like it should be followed to the top, right? So the areas keep on increasing. You can see the larger negative numbers are closer to the top, but you cannot see 3.6. It stops at negative 3.5. And it says that if you have lower or larger negative values, then your areas all could be treated as 0.0001. What does that mean? Well, it means that areas are going to be very small. Please notice they weigh less than 1%. So we treat them all the same. So we say they're all 0.0001, so pretty much nothing. And that's the reason why they say it's going to be same, because even if it's a little bit lower than that, that's what, 0.00001 or 0.00001. So it's really irrelevant. It's all pretty much same as a 0. So that's the reason why they don't continue to produce those tables for us, because the areas are so small that we usually say are zeros, because in statistics, remember, we don't really use 0. We say it's pretty much the same as 0, but that means that no chance for that to happen. So some values are beyond are not being really considered, which is interesting to realize, right? So areas beyond sometimes happen. And once again, what I do is use my places of hundreds and places of tens and see where they meet. Row meets the column, and on that place we get the areas. So that's one way of using these tables. And it turns out there is another way of using the tables by looking at the areas to go back to the z-score. So instead of selecting the row and a column, I could find the area, and by using that area, see which is going to be the column and the row where I found that area at. So it's like a backwards process, and every once in a while we are going to use this method as well. So what I'm going to do is another exercise to illustrate this. So I guess the next group of problems should enable me to show you that. So for example, where they want to get the particular z, like for example, like 37 percentiles. We already saw this a while ago, the percentile, or in exercise 37, they ask about 90%. 90%, which is going to be, well, pretty much everything. So like here, 90% of the area under the curve, which could be treated as 0.9, 0.90, or let's see, Alex, how many zeros you want? Well, I put it on purpose because 90% could be treated as 0.9 and 4 zeros for the area, and using that among the areas, I should be able to see the z that will cut out that 0.9 with 3 zeros that follow. So I'm gonna take a look at the tables again and notice that the areas, so now I don't use z-scores. Now I need to find the z-score. I look at those areas and I notice they start to increase, like 3, 5, 7, so they keep getting larger, 63, right, 380. I need to get 0.9, not 0.9, but 0.9. So I just keep going lower and lower. And I notice the largest I get is 0.5, which means that I have to move to the next table. And that's not surprising because it's definitely going to be something positive that I need, because 0 has to be in the middle, right? So the z is going to be positive. So the positive z-scores, please notice they keep going up higher and higher, and eventually I see 0.9. And that's 9, 0, 3, 2, and 4, 9. So they keep on increasing. So what's the lowest? What is the closest to 0.9, or to what I wrote as 0.9 thousand? And looks like I should jump up in the previous row and notice that 0.9 has to be someplace in between of 8997 and 9015. You see that? So the question is, which one is going to be closer? 8997 or 9015? Well, looks like the closer should be the closer to 0.9, or 0.9 thousand. Has to be one with 97, because if I subtract 3 10,000ths, I will get here. But to get there, I need to get 15, right? Because to 9,000, I need to add 15. So that's much larger. So that's the reason why I will take the previous value, which is going to be closer, right? And what is going to be the z-score? So that's the number I found, the closest to 0.9 or 0.9 thousand in my tables. Well, the row needs to be added to the column. So it's 1.2, and then I need to also attach 9 hundredths to it. So we went backwards, up, above, and to the left, and we saw that z-score 1.29 is the one they call as 90th percentile, P90 from the tables. And if I go back to the textbook, I'll see that this is exactly what they asked us to find in exercise 37, 90th percentile. Okay, so the bottom 90%, so the lower 90%, so higher 10%. So it's not the situation we're gonna see every single exercise, but every once in a while we will encounter such cases. And that's, I think, very interesting, right? I say, Alex, why don't we do one more, like number 39? All right, why don't I try to do it again? For problem 39 that says, how about 5th percentile? So find a reading that separates 5th percentile or the lower 5%. So it's going to be someplace on the left side. So percentile always on the left. So lower 5% or 0.05, right? That's 5th percentile. So the question is, what will be the z that will correspond to this 0.05? Or I can turn this into 0.0500, because again, our areas are all given with respect to this 4 digits after the decimal or significant digits, they say. So they all like point and then 4 numbers, right? 10,000ths. I say that's not 0.05, Alex, that's 0.5. You definitely need to use negative z tables, right? With the negatives, and looks like I need now to find 0.05 on it. So please notice the convenience is that the numbers are actually arranged from the top, from the smaller you scroll down and you go to the larger, and 0.5 I can see here, but again, looks like it's not 548. I need smaller, so like 537 is smaller, 526. So it gets smaller, smaller, and smaller, and it actually is going to be right here. In fact, they put an asterisk, which means it has to be right in between 0.5 and 495. Do you see that this is exactly going to be in between? So if I try to put 505, actually we can say it's a 0.5, okay, and then 0.495, then exactly 5 10,000ths will be to both of those numbers. So from 0.05 or from 500, if I add, I will go for the 505, sorry. Or if I subtract also 500, 10,000ths, it'll be 500 minus 5, 495. So the number we have is right in between, and that's the reason why they put this asterisk. So we need to put the number that corresponds also in between of 40 and 50, and that will be 45. You see, 45. So I actually have to attach 45 of thousands to whatever is in the row, which is negative 1.6. It'd be really minus 1.645, like that. And the reason why they put an asterisk is to actually help you to see this, as this number appears quite often. So if you go back, maybe I can clean a little bit of this mess. It's too much mess I created already. So clean the mess. So we'll better see what is going on in here. So we'll be able to see where this arrow that comes out of asterisk is actually going to. Did you see it already? It's traceable, and it is done on purpose because it brings you right to the number we just located here. It is 1.645 that cuts out that little area of 0.05 that is not shown in the table, but it has to be right in between. I say, Alex, why did they do that? Why didn't they take the closest? Yeah, we'll always take the closest, but there is no closest. That's the point. It's right in between, so we don't know if that's to the left or to the right. So that's why they averaged. So they went down to not 6.4 or 6.5, they went to 6.45. And that's what we're going to see every once in a while in this class from now on, because there'll be a couple of those asterisks. Turns out there's another one here, no more, just two of them, and we'll start to get used to it. So asterisks are here. Well, interesting. So what's the answer? The answer is here. The z is negative 1.645, just like that. So usage of tables for the z-scores is very interesting and exciting. And the key reason we need these tables is to find probabilities, to calculate probabilities of everything, because once again, we're dealing with normal distribution. Everything around us distributed normally. So we'll be able to find just about any answer. And I just want to give you an idea why I say any answer, and it's given to us by a very special formula that deals with so-called z-score calculation. And it turns out the way we do it, maybe I'll clean this everything here. So share this again. Okay, that's better. So we're going to be able to get any distribution whatsoever, any normal distribution. So mean could be anything at all, and a standard deviation. And then we'll be able to convert it to what we have for our tables, to the standard normal for the specific case where it's mean equal to 0 and standard deviation equal to 1. So standard deviation could be anything, but we have tables for that particular story. So we'll be able to do this conversion using formula for the z-scores, which is x minus mean or standard deviation, which is very powerful and quite an amazing fact. And my goal now is to show you that there's nothing really amazing in it. It's pretty straightforward. And I saw an interesting exercise that will give you a good intuition why this is working. So if they look at the next section and say, how about if mean is 100 and standard deviation is 15? So mean, the average is 100, and the standard deviation, the level of spread, is equal to 15. Then how about if you want to find the probability that something is less than 115? 115, if I want to put this on the picture, it is definitely to the right from 100, right? 115 is bigger. And the question is, find the probability that something is less than, right? Less than 115. So I can say it's probability that x less than 115. I say, wait a second, you used to have a z. Yes, I used to have a z for standard normal distribution that I'm going to need to use now. So that's z-axis. But in general, with any mean and there's any standard deviation, we have distribution and the x-axis and y-axis, as usual, we utilize. So the point of story is how to convert this 115 to a z-score that will give me exactly the same area, and that area I can find in the tables. And the answer is, here is the way to convert it, z-score formula. So to find the corresponding z-score that will give me exactly the same area, so exactly the same probability, and that probability I need, I'm going to need to take that value of x, which is 115, and then subtract from it mean, which is 100, and divide this by the standard deviation, which is sigma, which is equal to 15. And please notice when I do this, I'm going to end up with 115 subtract 100 is 15 over 15, which is 1.
1, yeah.
So it turns out that we have found how many standard deviations. Let me clear this. 15 over 15, which is exactly equal to 1. And we'll see what the z-score actually means. So 115 value of x with standard deviation equals to 15 will mean that we have exactly one standard deviation, right? If I took 15, and if I looked at 115, it'd be exactly one standard deviation away from my average, from my mean. So in a case when my standard deviation was 1, well, it has to be 1, and that's what we found. How many standard deviations were away from our center, from our mean, and that's exactly what the z-score shows. So number of standard deviations. And of course, now I can find this result by going back to my favorite tables, and I need positive tables, so I need to go for the lower part. And now my z-score is 1, right? Or 1.00, because I really need to know how many hundreds I have. Well, I don't have any hundreds. No hundreds means 0 of those hundreds. And 1 is right here. So the number is 8413. So the probability is going to be the area 0.8413. How about that? One step away from my center, 1 standard deviation. And from the tables, I get the answer. So the area is going to be whatever we just found, 8413. So that's the probability and for this to happen, 8413. And for the one above as well. So these areas are the same. And that's the key point of conversion. So we now can find probability of anything, just need to convert it to the standard normal, because now we'll be able to use those tables. Maybe I'll stop at this stage, give you a little bit of time to observe that without the stress. It's kind of too much, and then we'll do more, and we'll do more and more and more of this, and you'll see that eventually that we keep doing the same thing in every single exercise. It's very powerful information that you just saw. So, well, have a great weekend. I hope you will fully enjoy. So I just did exercise 1, but of course we need to do more, and I guess I'll let you enjoy the weekend, recharge, and we'll do more, right? So I'm going to stop to record. And